Hello everyone and welcome to this YouTube video on the channel of the Italian Association of Volcanology. My name is Roberta Spallanzani. I am a PhD student in mineralogy at the University of Potsdam. In this video, I am going to present part of the results of my PhD project that has been funded from the DFK organization in Germany. I am working in collaboration with the GFZ Helmholtz Center, the University of Göttingen, and the Laboratoire Magma et Volcan in Clermont-Ferrand in France. And first of all, I want to thank to all of these institutions for supporting me and helping me in order to finish my project. Here, I am going to present experimental insights on lithium and boron behavior during magma degassing. It has been deeply studied in the past that volatile elements can strongly affect a long list of processes taking place in the magma chamber and the volcanic conduit, such as magma fragmentation and eruption style and dynamics, particularly in terms of explosivity of a volcanic eruption. Lithium and boron are two of the components of this volatile phase. They are present in volcanic environments as minor elements. They both have two stable isotopes in nature, and they are particularly interesting because they are fluid mobile elements. This means that they are strongly related to the concentration and migration of water in the system. In the past decades, they have been used as tracers of water-related processes in subduction zones. But in my study, we want to apply this property to volcanic systems. So the main goal of this study is to understand if and how we can use lithium and boron to trace the speed of a magma ascending to the surface, and therefore use the two elements as a geospeedometer for magma ascent rates. To do this, we first synthesized our starting material, which is glass powder of rhyolitic composition. We decided to not incorporate any iron nor titanium in our glasses in order to avoid unwanted crystallization. Then we doped two different batches of this synthetic glass with 4 weight % of distilled water and different amounts of lithium tetraborate in order to get two end members, one enriched and one depleted in lithium and boron. For the entire set of my experiments, we used an internally heated pressure vessel, which allows experiments at high temperature and high pressure. The pressure medium is argon, and the maximum pressure is 1 gigapascal, while a maximum temperature is 1250 degrees. But the interesting feature of this machine is the possibility to perform a very fast rapid quench, with a cooling rate of about 150 degrees per second. The capsule is positioned at the hot zone at the top part of the sample holder, held only by a thin platinum wire. When we want to stop the experiment, we melt this little wire and the capsule immediately falls down to the bottom part of the sample holder that is at room temperature. During the experiment, the temperature is continuously controlled by thermocouples of the type platinum-rhodium. We performed two types of experiments. The first one is a set of diffusion couple experiments, where we put the two end members in contact in the same capsule and different conditions. And after some time, the two elements start moving in the space from one side to the other of the capsule. We used a temperature range between 700 and 1250 degrees and a constant pressure of 300 megapascal, while durations went between 0 second and 24 hours, where the 0 second duration means that the experiment was immediately stopped as soon as the machine reached the target temperature. The second set is a series of decompression experiments. In this case, we kept the capsule at initial conditions of 300 megapascal and 1000 degrees for 48 hours in order to homogenize the material inside the capsule. Then we started continuously releasing the pressure until 75 megapascal, keeping the temperature constant. In this case, the aim was to trigger the bubble nucleation and growth, changing the decompression rate at every experiment. Then we analyzed the samples after the different experiments using a laser ablation ECPMS and secondary ion mass spectrometry. The first result I want to show you are the diffusion profile, here shown for lithium in blue and for boron in red. We can immediately see a big difference between the two elements. At 1000 degrees and with a duration of 0 second, we see that lithium diffusion profile already takes a big part of the length of the entire capsule. It means that lithium diffusion starts long before reaching the target temperature. For boron, the length of the profile is a few hundreds of microns even after 24 hours at the same temperature. For each experiment, we modeled the diffusion profile, and we could calculate a diffusion coefficient that describes how fast this element migrates from one side to the other of the capsule. The calculated diffusion coefficients of the two elements have 4 orders of magnitude of difference, from 10 to the minus 10 for lithium to 10 to the minus 14 for boron. Then we had a look at the isotope ratios. In this case, for both plots, the dashed line represents the average isotope ratio of the starting material, and the gray area is the uncertainty related to that measurement. The lithium plot can be explained because 6 lithium diffuses faster than 7 lithium. For this reason, we can see the sinusoidal curve that gets wider and wider as long as the diffusion processes. With the model here represented by the blue line, we could calculate the coefficient beta that describes the relation between the diffusion coefficient of the two isotopes. In the case of boron, these are only preliminary results, and they show very small or no isotopic fractionation. But in this case, further measurements and interpretation are currently ongoing. The diffusion coefficient is temperature dependent and can be expressed in this Arrhenius plot. Here, the slope of the linear regression represents the activation energy, that is the minimum energy that the system needs in order for one element to start moving from its own spot. I compared my results that are respectively in blue for lithium and red for boron with the existing literature shown in both plots in gray and orange. In gray are shown the available data in dry systems, while in orange are the results of Holycross et al. 2018 for lithium and Mangal et al. 1999 for boron, that are the only studies with similar experimental setups and particularly with hydrated conditions. The comparison with these two studies highlight that the activation energy that I calculated in my study are very similar with Holycross and Mangal. In both cases are significantly lower than the one calculated in dry systems. And this means that when water is in the system, both elements, lithium and boron, diffuse faster. While the shift could be related to a pressure effect, as both Holycross and Mangal use higher pressure compared to my experiments. Once we have set the time window in which the two elements are subjected to diffusion, we could set the parameters of the decompression experiments. The first results come from the simple observation of the samples after the decompression. The bubble size and distribution directly depends on the decompression rate of the experiment, going from the right picture with a high number of very small bubbles with a decompression of 30 minutes to the left picture of 10 hours of decompression with very few but very large bubbles. These observations are confirmed by plotting the calculation of the bubble number density with the decompression rates of the experiment. Here, my data are shown with these blue triangles, while the circles of different colors are showing the existing literature. And my data seems to have comparable slope with Hamada et al. In 2010, even though they used lower temperature and initially saturated condition, which is not the case for my experimental setup. After the simple observation, we made analysis again with the SIMS and laser ablation ECPMS. First of all, we wanted to pierce a bubble that was closed underneath the surface of the sample. And here you can see the outcome. The plot shows the raw signal of the ICP-MS against the time of analysis. We started ablating the glass on the same spot until we reached the bubble and we opened the bubble. And this is what we see in the plot. Then we looked into the area surrounding the bubble. In this case, I will only show you the boron data, but lithium exactly the same behavior. Starting from the dashed line that represents the average concentration of boron in the starting material, we can see how boron concentration decreases progressively, going towards the bubble that is represented by the blue area. We also analyzed the isotopic ratio, but in this case, there was no visible isotopic fractionation. We are still trying to understand if we don't see any variation in the isotopic ratio because the exsolution of lithium and boron comes at equilibrium, so there is actually no isotopic fractionation, or if we somehow lost the information during the experiment or the analysis. To sum everything up, lithium and boron in hydrated silicate melt diffuse faster than in dry conditions. Lithium diffusion is very fast and starts around 600 degrees centigrade, while boron needs hours to days in order to produce a significant diffusion profile. During decompression, the two elements are incorporated into the bubbles, and this results in a decrease of lithium and boron in the area that surrounds the vesicles. The extension of the area subjected to this decrease depends on the decompression rate. The next step to conclude this work are further SIMS measurements, especially on decompression samples. And currently we are developing a model that combines all these informations all together and express lithium and boron exsolution into the bubble as a function of the decompression rate. And this will give us direct information of the magma ascent rate. So here I conclude my presentation. I thank you very much for watching this YouTube video, and please feel free to go on the YouTube page of the Italian Association of Volcanology, which I want to thank for this opportunity, and take a look at the previous videos. Also have a look at the web pages of the University of Potsdam, the GFZ Helmholtz Center, the University of Göttingen, and the Laboratoire Magma Volcan, because they are amazing institutions and they are carrying on very interesting projects and studies. Again, thank you very much, and goodbye.